Hi, and welcome to Allen High School's discussion of kinetics, the rates of reaction for AP and IBHL1 chemistry. Now, we're going to start our discussion by taking a look at 3 questions that we ask about chemical reactions. And those 3 questions will be dealt with in the next 4 units that we'll be covering. So the first question is, will a reaction proceed spontaneously? Now, this chapter is going to address much more than just spontaneity of reactions. We'll look at heats of reactions and the work available, the energy available to do work, and things such as that. But one of the key issues that it brings to the table is, will a reaction proceed spontaneously? And that's a conversation covered in thermodynamics. Now, I actually cover thermochemistry, that's enthalpy, at the same time. So that's thermodynamics. The next question says, how far will it go? Again, we've spent our time discussing so far reactions that proceed 100% to products. And that field of study is called stoichiometry. And you know how to do those calculations, and I promise you, you won't forget them because we'll be integrating them into our conversations as we go. Now, there are other reactions that proceed less than 100% because they're reversible. Now, reversible reactions are covered using the mathematics of equilibrium. And again, we had a little brief introduction in pre-AP to these things. Well, a lot on stoichiometry and some on equilibrium. And I really think it'll come back to you pretty well. Now, the next one is what we're doing in this unit. How fast will it go? And that's kinetics. Now, there's a pretty tight mathematical relationship between equilibrium and thermodynamics. And frankly, we'll be using stoichiometry in that as well. But the link to kinetics is weak. And it's quite common to ask questions saying, well, you know what? A reaction proceeds spontaneously without external intervention. And then it'll suddenly say, well, why is it slow if it proceeds spontaneous? Well, spontaneous doesn't tell us how fast a reaction goes. It tells us that a reaction will go without much outside intervention or addition of energy. You need a spark to get it going, but we'll talk about that in just a minute. Now, for kinetics, it's quite different. Reactions can occur spontaneously and take 10,000 years. I'm thinking of some nuclear decay. All right, so kinetics and spontaneity have a much weaker link, and questions want to find out if you understand that link. Now, let's move forward here, and let's take a look at a brief review of collision theory. Now, in collision theory, we have 3 premises that we want to link to our observation. The first is that molecules must collide in order for a reaction to occur. Again, I hate to bring it up again, but Denzel is not going to fall in love with me unless we meet. We have to collide or meet in order for that reaction to occur. The second is that molecules must collide with sufficient energy. That's we're going to be talking, that's kind of the spark that has to get it going in a reaction, sufficient energy. Now, for some reactions, that spark that gets it going is all it needs, and then the energy from the reaction perpetuates the reaction. Other times, you have to continually provide energy. Now, that sufficient energy is called the activation energy. E sub A is the symbol used there, and we will be using the units joules or kilojoules on a regular basis. And the third is that molecules must collide with the correct orientation. So in a relationship that is going to have promise, hold promise for a future, there has to be some sort of energy, some sort of attraction involved there. And there's a variety of analogies for this last one, but one I think about is if someone's religion is very important to him or her, often it's pretty critical that you marry and date people of that same faith. If a religion is really important to you, if your faith is very important to you, you need that commonality typically to make a successful reaction or bonding situation occur. Now, let's take a look at a couple of pictures that I think will help you get this. All right. Now, this is called a potential energy curve. And that's because we're looking at potential energy increasing on our y-axis. Now, our x-axis is a very vague course of reaction. We're just monitoring the reaction. It's not a quantitated axis, course of reaction. Now, what we would do is we'd put R here. So this is my potential energy of my reactants. These would be my products. And then if you kind of brought a line over here from products over to the axes, then we would have our energy of our products. Now, on this, we have something up here called a transition state or an activated complex. And that is a point at which the bonds that are going to break are partially broken. The bonds that are going to form are partially formed. And it's committed to going to product. That's key. It's committed. So both of these are partial. Remember that partial positive, partial negative. I'll use that symbol there for us. It's committed to heading on to the product. Okay? Now, the activation energy is the difference. If we went over to here and brought our line over, that would represent the energy of our activated complex. Well, our activation energy is the difference between those. So the activation energy for the forward is going to be the energy of the activated complex minus the energy of the reactants. Now, we could do the same thing for a reverse reaction. So the energy of the activated, or the activation energy for the reverse reaction would be the energy of the activated complex minus the energy of the products. Now, technically, this is a difference in energy, isn't it? But people just don't do that. It's assumed that we get it. So if we look at this graphically for our reactants in our forward, that difference, that delta, represents the forward activation energy. Now, if we wanted to do it for products, we would only go down to the product line, and that difference would be the activation energy in the reverse direction. And you notice they're both positive. We don't ever have a trough in these. Now, we've seen this before. We're not going to talk about it much, but as long as we have these, that difference there, my energy of my products minus my energy of my reactants, is the enthalpy of the reaction, delta H, enthalpy. It assumes a particular conditions in terms of pressure and volume and that forth, but that's what we're going to be dealing with primarily in this class, is enthalpy. And since in this case it's negative, that means it's exothermic. And what that would mean in terms of an experiment is your surroundings would get hot because the reaction is releasing heat. Those are things we've talked about, but I think it's good to connect them at this point as well. All right, I found a great picture for orientation, and I hope that's not too distracting. I've not tried it this way on slide projector view, but we're going to give it a shot. So in this case, we have a situation where we're going to take a halogen, and we're going to add it across this. This isn't totally clear to see, but that would be a double bond. And I know it's a double bond because each carbon needs 4 bonds. And right now there's 2 hydrogens, then that. So this had to be a double bond. So this could be, actually this could be a hydrogen and maybe a bromine. And what the reaction is, the goal of the reaction is to add those across the double bond. Now, in order to do that, this molecule needs to collide at the bond in this direction. That collision, assuming enough energy, sufficient energy to overcome the activation energy, would lead to a successful reaction. If you look at all these other possibilities, this one's backwards. It reacts best with the hydrogen. So that's backwards. It's not going to work. This one's coming at the wrong angle. It's coming towards the hydrogen rather than at that double bond. And then this one's coming from the opposite end of this carbon, again, rather than at that double bond. And so in this case, only one of these collisions would lead to a successful reaction, always assuming correct energy to overcome, or sufficient energy to overcome that activation energy at that point. So those are our 3 premises. Now we're going to ultimately link those to the factors that affect the rate of a reaction. But for now, I think we need to move on to our next video, and we're going to start with the mechanisms first. It's an unusual place to start. I read an article by Lisa McGaw on this, and I wanted to give it a shot. Also, I wanted to point out as we get going on the variety of videos that the page number of your notes is in the bottom right-hand corner. So hopefully that will help you track with the notes in the video much more effectively. So we're going to move on to the second video. So until you turn the video on again, this is signing